Hello everyone, it's my pleasure to present our work here. The work is using vectorized execution to boost SQL query performance on Spark. My name is Shen Yijie from Institute of Computing Technology, Chinese Academy of Sciences. First of all, we all know that the pursuit of high-performance query processing is endless. We people never get satisfied with data processing speed. Firstly, we got general-purpose database management systems for structured data analysis. Then we've got OLAP systems such as Hyper, MongoDB for more advanced analysis. Then, as the data we processes grows, we've got SQL and Hadoop systems such as MPP systems or MapReduce-based SQL engines to process the large amount of data among the distributed cluster. Given the state-of-the-art MapReduce SQL engines as a Spark as an example, the speed itself is also accelerating among the years. It is about 3 times faster than its first release in 2016. When we take a look little further into the execution engine, we know that the physical operator is the basic execution unit. As an SQL query enters the execution engine, it gets analyzed, optimized, and finally evolves into a physical plan tree. The simple SQL get transformed into an logic operator tree composed of filter, project, sorts, join, aggregates, and then it is finally translating to a physical plan shows how SQL get executed, such as how data distributed over the tasks, and also how intermediate data get transformed over the different stages of the tasks. Then we know the execution model for physical operator really matters. First of all, the original vanilla volcano model is poor for its incurring too much function call and too much branching. And also for data-centric compilation, the pipeline operators are compiled to the nearest pipeline breaker operators, which takes in register processing in mind. However, it doesn't accelerate or optimize the performance of pipeline breaker operators, so we think it's not idle for our work. Then we think about vectorized execution, which compose all the operators into the vectorized processing logic and keeping in-cache processing in mind. When we want to first do the proof of the concept, we first break down the existing Spark SQL execution time on the TPC-H benchmark. We do a breakdown and witness a spread of time over 3 kinds of operators or operations, i.e. the simple operators such as filter and project takes about 13%, shuffle takes about 21%, and complex operators such as sort, aggregate, join, this kind of operator breaks the processing pipeline and takes all the input records into account, then it can emit its results. And when we do our first approach in Vectorized Shuffle, the performance is bad since the amplification of shuffle data footprint with too much metadata inside. And when we think about complex operators, the existing implementations incurs too much random memory access, then therefore has bad performance. And when we think about simple operators and complex operators both, in vectorization execution mode, the state-of-the-art mode engines always select settle down batch length, which leads to suboptimal cache CPU cache utilization and therefore bad performance. When we have all this in our mind, we came up with a V architecture that composed of two parts: the query planning part and the below the query execution part. We write Spark's generated physical operator tree into all composed of vectorized operators. Then during the execution, all the operators execute in vectorized mode, such as vectorized projection, vectorized filter, and vectorized reader. And during the data shuffle among different stages tasks, we also use the vectorized shuffle, which is efficient and performance well. When we first implement the execution engine of we identified that the data structure that in memory during processing and during storage is really matters. Taken on several in vanilla Spark as an example, it is targeted at high performance CPU friendly processing, therefore it is 8 bytes aligned. However, when the structure is used to store the data in memory or in files, the blankets, as we shown above, became very significant and takes about much time during data compression and take much space in the whole structure. So we came up with our record batch representation. We divided into two representations, one for runtime for CPU cache CPU friendly processing, and one for in-memory disk storage for better compression ratio and higher processing friendly. When we do vectorized shuffle, we came up with a serialized-aware assembling technique that when we merge different vectorized batches, we just merge the metadata and just concat the data parts untouched, which with this method we can significantly reduce the footprint of metadata parts, as shown in the picture. Then when we implement sort algorithm in V, we came up with rearrangement technology. When for the naive sort, it is first sort each batches in cache. However, it gets the real data unchanged. When it comes to partial merge phase, the data are randomly accessed among the whole memory, so the access pattern is very bad. The RBR algorithm we came up with is quite advanced. When we have just done in-cache sort here, we just materialize the real sort into the storage. I will do real data rearrangement here. When want to do the partial merge, the data access pattern we got is multi-segmental sequential accesses. Therefore, the random memory accesses are greatly reduced. And also we observed that only part of the operators or only part of the vectors are used at a time during computation of complex operators. So we came up with the operator-aware batch length algorithm and set batch length at operator-wise. Then we come to our experiment part. It is we are evaluating our work using TPC-H or 22 queries using a 4-machine Spark cluster with 1 TB data. First of all, we can see that the shuffle performance improves execution time up to 1 times and 64% on average than Spark. And also we greatly reduce the data footprint by up to 51% and 29% on average compared to Spark due to serialization-aware assembling. And for sort performance, we can see that the partial merge with rearrangement saves 47% time on average compared to the counterparts without rearrangement. And the spill time influence of the sorts shows that spilling only takes 13% of total time on average, benefit from our compact batch layout. When we test about the batch length influence on the sort operator, we saw that it comes to its best performance when it reaches 128 kilos records. And this is the overall TPC-H performance. We witnessed that the performance speedup of V against Spark is up to 72.7% and 25% on average. That's all. Thanks for listening. Thanks.